Okay. Wait, let's get the show on the road since this is live streamed. We want to be on time, don't we? So, first off, we will put the first hat on, and that is the guy in charge of senior experiences. So, thank you all for coming to support the speaker. Really appreciate that. We also want to thank Alex for live streaming, so he's here to do that even on this bright, beautiful, wonderful day. We still have another 10 of 25 lectures left, so if you want to come and support other friends. Okay, there's one tomorrow at 11:10. And then 2 more on Friday starting at 3:10. So Mike is going, me and Jim is going to be talking about his teaching experience with 8th graders, which is always very interesting. Anyhow, so encourage you guys to come. Also, if you've missed it, you can see it on YouTube. She will be in all of her YouTube glory shortly thereafter. If you go to YouTube and search Chemistry Senior in Lawrence, you can rewatch it thousands of times. She's excited about that.
Yeah.
Anyhow, now we will put introduction hat on. So it's been a pleasure having Ellen as an advisee, even for a short bit of time. She originally was Juan's advisee, and Juan sadly moved off to Skidmore, but she stayed with us, and so have enjoyed having her in class. And it's sad to see her leave, but very excited because we're sending her to join 2 other Laurentians in Iowa for graduate school, and so that's really great. And then I know she wants to take after Dad in terms of and Mom in terms of chemistry. She always tells me very fond memories of sitting down below here, listening to Dad lecture and draw all kinds of chemistry stuff on the board, and that clearly had some sort of very important influence. And so I can only hope my 14-year-old will come away with the same sort of ideas.
Child abuse.
Pardon?
Child abuse.
Child abuse, yeah, that's what my 14-year-old thinks of it now, but hopefully it'll get better than that. Anyhow, without further ado, we'll turn it over to Ellen.
Okay, so as Dave just said, I'm Ellen, and today I'll be talking about my research that was on the photochemistry of chemisorbed nitrate on different components of tropospheric aerosols. And so to start, I'll break down the title a little bit, and there are 3 main parts to our research, and that is the photochemistry, the nitrates, and the aerosols. And so to start, I'll explain what aerosol particles are. And so aerosol particles are small solid or liquid particles suspended in the atmosphere that can absorb and reflect sunlight and affect the environment and the climate. And so to kind of put it in perspective how small these aerosol particles are, you can see in this image noted in blue and in red, these are the aerosol particles, also known as particulate matter, which are noted as PM. And you can see that not only are these aerosol particles smaller than a single grain of fine blue sand, they're also smaller than a piece of average human hair. And you can see that the ones in blue, those are the PM10s. That means that these aerosol particles are smaller than 10 microns, and those are mostly responsible for atmospheric visibility. And then the ones in red are the PM2.5s, and these are aerosol particles that are smaller than 2.5 microns, and they mostly are responsible for health effects. And so because these aerosol particles are so small, they can easily be carried through the atmosphere from a variety of different sources. And so first are anthropogenic sources, which means that they're man-made, and the majority of aerosols from man-made sources come from industrial and automobile fuel combustion, specifically fossil fuels and diesel fuels. And automobiles, incinerators, and power plants can produce sulfates, nitrates, organic and black carbons, volatile organic compounds, or VOCs, as well as other particles that get emitted into the atmosphere. And that's what you can see here from this image of a power plant. And then biomass burning is also another source of aerosol particles. Additionally, deforestation, overgrazing, drought, and excessive irrigation can alter the land surface, increasing the rate at which aerosol particles can enter the atmosphere. And because these are man-made or anthropogenic sources, they're more easily regulated. There are also natural sources of aerosols, and the bulk majority, about 90% by mass, of aerosols come from natural origins. And so the first type is mineral dust, which can come from sandstorms or dust storms, and those mineral particles are whipped into the air by strong winds. and then biogenic volatile organic compounds from vegetation. And the way that these BVOCs work is that they can either interact with one another in the atmosphere to form a particle, or a BVOC can interact with another particle in the atmosphere to form a new particle. And then wild forest fires introduce particles into the atmosphere, specifically organic carbon and black carbon. And then volcanic ash, and because these volcanic plumes can reach so high up in the atmosphere, volcanic ash can actually circumnavigate, which means that it can travel around the world multiple times. And then there's also sea salt, which comes from sea spray or when waves break in the ocean. And so to kind of show you how aerosol particles can move throughout the atmosphere, this is a video that I'll put in a second. And what you should note with this is that in red, those are mineral dust particles. In white, here and here, those are anthropogenic aerosols, so man-made ones. And then in green, in South America and Central Africa, those are biomass burning. And then in light blue, across the bottom or near the poles, you'll be able to see that's sea salt. And so, if I play this. So you can see that this is showing intercontinental as well as long-range transport, and you can see a dust storm in the Saharan Desert traveling across the Atlantic Ocean. And this is over a 3-month span in 2006. And you'll note that the anthropogenic sources of aerosols are higher in areas with higher industries. And so the aerosol particles have a lot of different effects on the environment and the climate. And the first effect that they can have is through air pollution. And as I mentioned before, those PM2.5 particles, those are the really small ones. And those are regulated by, or most regulated by the EPA or the Environmental Protection Agency, because those particles are so small that they can reach the deepest crevices of your lungs and cause a variety of health problems, specifically respiratory issues. And then aerosols can also affect the atmospheric visibility. And the way, and those are the PM10 particles. And the way that those work are by scattering light in the atmosphere. And so you can see in this image down here, as you go from left to right, the amount of aerosol particles are increasing. And because there are more aerosol particles, the light is scattering more, decreasing the visibility. And then aerosol particles are a large component of the composition of clouds. And with that, aerosol particles provide a platform or a surface for chemical reactions to happen in the atmosphere. And they also affect solar radiation. And so the way that particles work as a platform is they provide a surface for heterogeneous or multi-phase chemical reactions to happen in the atmosphere. And then, as I just mentioned, they also affect solar radiation. And so this is a little diagram to show you how aerosol particles can affect solar radiation. And first, aerosol particles can absorb solar radiation as particles themselves. And then because aerosol particles are a large component to clouds, they can alter the way in which clouds react with solar radiation. And so some of that solar radiation will be absorbed by clouds, but some of it will also be reflected by clouds. And then, of course, some solar radiation will reach the Earth's surface, and some of that will be reflected. But overall, these aerosol particles have a cooling effect on the climate because they're reducing or limiting the amount of solar radiation that reaches Earth's surface. And so then the next main part of the title and the research was the photochemistry. And photochemistry is the study of chemical reactions that occur with the absorption of light. And so this can be any one species reacting with light to form another species as a basic overview. And so to kind of put this in perspective with our aerosol particles, it could be an aerosol particle with some sort of substance on the surface, and when light hits that, a photochemical reaction will take place, causing some sort of reaction and another product. And in our research, we were particularly interested in looking at how photochemical reactions with nitrogen species, specifically NOx gases, occurred. And so what are NOx gases? Nitrogen oxides are a group of gases that are composed of nitrogen and oxygen, specifically nitric oxide, or NO, and nitrogen dioxide, NO2. And these two molecules are commonly referred to as NOx because they go through such a rapid and dynamic cycling that it's easier to refer to them as one group rather than as two separate categories. And so again, nitrogen oxides come from a variety of sources. There are agricultural sources such as fertilizers and livestock waste. And then nitrogen oxides also come from automobile and fuel combustion, just like aerosol particles did. And they also affect the environment and the climate in specific ways, air pollution being the most predominant one. And one type of air pollution is photochemical smog. And what happens with photochemical smog, volatile organic compounds react with NOx and sunlight to create smog. And as you can see in this picture of Sao Paulo, Brazil, this grayish brown cloud hanging above the city is actually photochemical smog from this reaction between NOx and light and VOCs. And you will see higher amounts of smog and air pollution in places with higher populations because there's going to be more anthropogenic sources of aerosols and nitrogen oxides. And then NOx also are involved in the formation of acid rain. And with this, NOx can react with water in the atmosphere to form nitric acid. And in moderation, this can be good because nitric or acid rain can provide nutrients to the soil, but in excess it can be corrosive and harmful to the environment. And then nitrogen oxides can also form surface adsorbed nitrate on mineral dust particles, which I'll come back to in a second, so just keep that in mind. But first, this is a basic overview of how nitrogen sort of works in the atmosphere. And so NOx can be emitted from various sources where it goes into the atmosphere and undergoes water vapor and cloud chemistry to form nitric acid, which can then come out of the atmosphere as either wet deposition, which would be acid rain or acid snow, or it can come out as dry deposition, which would be just the particles settling out. So to kind of look at how nitrogen species, specifically NOx gases, react in the atmosphere, you can see that nitric acid can react photochemically to form nitrogen dioxide. And that nitrogen dioxide can then react to form nitric acid again. But nitrogen dioxide can also react photochemically to form NO, which is the other NOx species. And then NO can react in a variety of ways to form NO2 again. And one important reaction here to note is this reaction between NO and ozone, or O3, to form NO2 again. And this is particularly interesting because it's contributing to the depletion of ozone in the atmosphere, which can be related to the hole in the ozone layer. And so to kind of put both the nitrogen oxides and the particles together, you can see in this schematic that nitric acid is adsorbed onto a particle surface to form nitrate and nitrite, and those can then photochemically react to form our two NOx species, NO and NO2. And those can then further react in the atmosphere to form other nitrogen species. And in our research, we were primarily concerned with the formation of the two NOx species as well as HONO and N2O. And so in our research, our main objective was to examine how the formation of NOx gases formed from heterogeneous surface chemistry on metal oxide surfaces. And with this, we also wanted to look at how the concentrations of NOx gases formed changed over time. And so to do this, we had an aerosol particle surface, a nitrogen source, solar radiation to form a NOx gas. Experimentally, we had the surface with light, as well as a gas source and a detector. And for this, we use FTIR spectroscopy. And so this is a general overview of our experimental setup. But to start, I'll go over the metal oxide surface and the solar simulator. And so with FTIR, we use a germanium crystal for our metal oxide surface. And this was prepared by applying a methanol slurry of the metal oxide to the germanium crystal, which you can see here is the shiny part in the middle. And so then once that methanol evaporated, what was left was the metal oxide coating that surface, which you can see over here, that shiny part is now red. And that red color comes specifically from iron oxide. And so in our research, we looked at iron oxide, zinc oxide, aluminum oxide, and titanium dioxide. And so then we use these 4 metal oxides to sort of imitate what metal oxides we would see in mineral dust particles in the atmosphere. And so then once the metal oxide surface was prepared, a custom Teflon chamber with a quartz window, just up top, was screwed onto the metal oxide surface, which is here on the germanium crystal. And directly above that was a solar simulator. And the solar simulator shined light down straight through the quartz window onto the metal oxide surface. And so then the next part of the experimental setup was the gas chamber. And so in this gas chamber, air was bubbled through an acid solution containing nitric acid and through water, and then dry air, wet air or water vapor, and acid were mixed together in this mixing chamber, which was then introduced to the metal oxide surface in that Teflon chamber. And this was to create Chemisorbed nitrate on the surface of the metal oxide. And so then the last part of the experimental setup was the long path cell and the detector. And for this, we used Fourier transform infrared spectroscopy to detect the gases that were formed from our reaction. But before we could really detect anything, we ran into a little bit of a challenge. And that was, how can we detect low concentrations of products that were formed? And so we knew that with FTIR, you wouldn't be able to detect any small concentrations. And so to solve this sort of issue, we looked at Beer's law, or the Beer-Lambert law, which states that absorbance is proportional to concentration times molar adsorptivity times the path length. And we saw that the easiest way to compensate for small concentrations is by increasing the path length. And so that's exactly what we did. And if we were to have used a normal FTIR cell, the path length would have been only 10 centimeters. But what we did was we switched to using a long path cell. And with this long path cell, what happened was the IR beam was then bounced off a series of mirrors, which changed the path length from 10 centimeters to 200 centimeters. So if we look back at Beer's law, by increasing the path length, we were able to detect lower concentrations. And so then after we figured out this whole long path issue, we then carried out the full process for all 4 of the metal oxide surfaces to see what reactions actually happened. And so then we took our FTIR spectra and analyzed those, and we did find results, which is good. And so as you can see, this is the FTIR absorbance spectrum for aluminum oxide specifically, and you can see that we have wave number versus absorbance, and that the different colors and the different peaks represent the increase of time from time 0 to time 400 minutes. And the first peak that you'll notice, the most predominant one on the right, is that is for NO2. And then the second most predominant peak is for HONO, or nitrous acid. And then additionally, we saw smaller peaks, which you can kind of see here, here, and here. And those were for N2O, NO, and N2O4, or nitrogen tetroxide. And as I mentioned before, we also looked at how the concentrations increased over time as the reaction went on. And you can see that from time 0 in pink all the way through time 400 minutes, the concentrations or the amounts of products increase. And so that trend is a little hard to see with some of these smaller peaks, but if you zoom in on them, you can see that the same trend was observed, that as time increased from 0 to 400, the amount of products also increased over time. And so we saw the same general trend with all 4 of our metal oxide surfaces. And here you can see that we have aluminum oxide, zinc oxide, titanium dioxide, and iron oxide. And one important thing to note with these 4 graphs is, first, you'll see that the x-axis for all of them is still wave number, and the y-axis is still absorbance, but the scaling for these 4 graphs is different and ranges from 0.2 to 0.8, and that is telling us that the amount of products formed with each metal oxide surface changed. And so you can see, if you look at zinc oxide and iron oxide, the peaks look like they're the same height, but they're actually at different scales, and so there was a lot less iron oxide products formed with iron oxide than there were with zinc. But again, the same general trend of that nitrogen, NO2 and HONO were the most predominant products formed, and even though again it's a little harder to see with some of those smaller peaks, we saw that N2O and NO were formed for all four metal oxides, and the same trend of time increase, or the concentrations increasing over time, we saw that with all four of the products, or all four of the metal oxides as well. And so then if we come back to this diagram and think about what product or what reactions actually happen. And so in our research, we had nitric acid adsorbed onto a particle surface, which was our metal oxides, to form chemisorbed nitrate and nitrate. And those, and spectroscopically, we saw these different products formed. And based on previous research, we believe that these are the possible mechanisms by which the different nitrogen species were formed. And one thing that you'll note is that we didn't see any N2O2 formed, and that was not present in our absorbance spectrum at all for any of the metal oxides. And we believe that this is because N2O2 is relatively unstable and will rapidly react to form other products, and can therefore be considered transient species. And so then why does this really matter in chemistry or in atmospheric chemistry? And all the products that we saw formed have different effects on the environment. And so the first one that we saw for NO and NO2, those can contribute to the formation of acid rain. And like I mentioned before, acid rain can be a good source of nutrients in moderation, but in excess can be corrosive and harmful. And then we also saw the formation of HONO, which is the source of the hydroxyl radical in the atmosphere, and the hydroxyl radical can form ozone in the lower atmosphere and have an effect on the environment and climate. And then we also saw the formation of N2O, which was particularly interesting because it's a greenhouse gas, and the way in which greenhouse gases work is that they absorb radiation, altering the climate. And one interesting thing to know with N2O is that the impact of N2O is actually 310 times more than that of CO2, which kind of means that you can consider it a worse greenhouse gas. And so all of these nitrogen species that we saw formed came from the basic concept of a nitrogen, a photochemical reaction happening on the surface of an aerosol particle. And by further understanding how these reactions take place and form not only these nitrogen species in the atmosphere, but also how these aerosol particles can react and take place in atmospheric chemistry, can help better understand what chemistry is actually happening in our atmosphere. And by having a better understanding of that, scientists can then apply that to various issues like global climate change. And so I would like to acknowledge Juan Nevea, who is my research advisor on this project and made the whole project possible, as well as Dr. Dave Hall and Dr. Deanna Donahue for listening to me give this presentation a million times and helping me with it. And then also, of course, my parents, because they've supported me through the years and sparked my interest in chemistry. Any questions?
How does the free radical make ozone?
Which free radical? The hydroxyl radical? The HONO? HONO reacts in the atmosphere to form, I'm not entirely sure about the actual mechanism by which it does. That's getting more into the hydroxyl chemistry, which I didn't look at really, but it forms the hydroxyl radical somehow, and then that radical then reacts with other species in the atmosphere to form ozone. That kind of answered it.
Come on now, don't be shy. We've asked you all our questions over like There are no more questions. Thank
Well, I
you.
guess I
Oh,
do
oh,
have
there
one.
we go. She
So
got
can you go back to your data slide? Because I was just curious about the ratios. So did you see this? It doesn't. Do you have any idea why the different metals show different ratios of production?
We were not entirely sure. That was one thing that we were going to look at after testing some more metal oxides, and then look at what reasons there could be for the different ratios. So we haven't gotten into that part yet, but it is something that is on the table for the future. Yeah.
Related, possibly annoying question. How do you deal with standardizing this?
Which part of it?
The slide that you're showing right now.
With-
I mean, it looks quantitative, but how do you know that it's quantitative?
Like, how did we standardize like, the peaks?
Yes.
So this was basically, we had the full IR spectra, and I shortened it down to show the parts that had the peaks, and then, like, I guess, like, do you mean like why do they all look like they're the same height?
No, how do you know that it's really, say, 2-to-1 for aluminum oxide and titanium oxide? You have 0. I'm reading right, 0.8.
Oh, that,
0.4. So how do you know about those numbers?
Those are just arbitrary units that were, like, when the FTIR spectrum was shown on the computer, that's just the units that it had with it. So I'm not entirely sure where that came from. That has just always been with the data. But the point, like when I mentioned that the scales range from 0.2 to 0.8, those were the scalings of the peak intensities, I guess you could say. And so I'm not entirely sure like where the standardizing comes from with that.
What are those rollable amounts anyway?
Yeah.
Okay. That's the answer.
Okay.
Thanks, Dad.
Other questions? Okay, let's thank our speaker again.